Recording has started, so I'll share my screen. Hi everyone, uh, welcome to the data structures and algorithms, which is part of the PG Diploma AI in AI and data structures and algorithm. There'll be 7 sessions. Uh, so when we started with section A for computer fundamentals, followed by C language, session 1-6. We now move to PG Diploma AI Core as data structure are key to algorithm and modeling in AI. So we now have a coverage plan, like we jumped into C and did something on the uh, uh, coding and all. We similarly, before moving to Python, Java, etc., object oriented, we wanted to make sure that we cover the data structure with C, because we started with C. And so uh, C is more like, or C++ is more like C, and it has object orientation. So we will use mastering algorithm with C by Kylen Loudon of O'Reilly publication as our reference book. And we'll start with, we'll skip 1, 2, and 3 chapters because they were covered under C when we started in the C session 1 to 6. So we'll focus because that contains something like recursion and loops, and which are already covered. So what we plan to cover is start with chapter 4, which is analysis of algorithm. Chapter 5, linked lists. So we'll try to cover 4 and 5 today, and then onwards we'll cover uh, all the data structures, including stacks, queues, sets, hash tables, tree and heap and priority queue, which will cover all the data structures, at least the major data structures. Following that, we will start with the uh, what you call the algorithms, which will cover the sorting, searching, numerical method, data compression, encryption, graph algorithm, geometric algorithm, etc. So by and large, we'll try contain within 7 sessions unless we need to slow down for reasons for understanding. So before I give the handle to Jaymeet, I'll just try to cover the analysis of algorithm as he will be focusing on the data structures. So what is an algorithm? So you have a process or a set of rules that need to be followed to do the calculation, like we do in flowcharts, etc. So it's a problem solving operation, especially when it is run on a executed on a computer. So what are the criteria when we design an algorithm? Examples of algorithms are functions like search, sort, uh, many more, garbage collection, etc. in the computer in terms of memory usage. And so what we do is, how do we design? And if we design, what is the first thing? First, we need to address the problem. Example, if you say sorting, then functionally it must address the sorting. Whether you are doing a quick sort or whether you are doing a linear sort or whichever, whatever functionally it should satisfy the function. Then we come to how fast does it run on a computer? So that relates to performance and efficiency. Then the last, what is the amount of storage does it consume? So it depends on the data abstraction and organization of data, and that's where the data structures play a key role in algorithm, and that is one of the criteria. So are there any formal deterministic method to evaluate algorithm? Yes, they are based on functional performance, abstraction, and efficiency. So how do we describe that? If a problem, like example, garbage collection, has many algorithms, you can use what you call the recursion to recover the memory. You can allocate dynamically memory. There may be many algorithms. But how do we formally analyze this algorithm? So there are three measures we focus here, and that will be worst case analysis, O notation, and computation complexity. Let's come worst first comes to worst case analysis. So example, if I have a set which has 13752468009 is a set of numbers, and try to search one, it will be first. So when we run a search, it will hit in the first element. If it is 9, then it will hit in the last, which is 10th element. Now if I search for 5 or 4, 5, it will be 4th element. So this shows that linear search depends on what we are looking for. So if we search for 10 and the answer is we won't find any such element in the set, because so there can be many consequences, many outputs depending on the search we do. So we may find the best case example 1, worst case example, it could be either not found or it could be 9 in this case. And the average cases, it could be anywhere between 2 and 9. So to ensure we are looking for the right element, we need to restrict the algorithm. So if we restrict the algorithm to only single digit number search, then 10 will be eliminated, or anything beyond 1 digit will be eliminated. So algorithms can be constrained to look for certain elements, example search, right? So what we have done is, with the restriction, with proper restriction that we don't do invalid searches, we can have the worst case as the 10th element. So thus we have analyzed the search, worst case analysis we have done. Why should we do worst case analysis? That is the question. So many algorithms like linear search we looked here. Worst case is important to get the upper bound on time, R steps or frequency of occurrence. So best case or average case do not give much insight into how the algorithm performs. In linear search, when we get a case 1, first element, it tells nothing. In the case of average, we are confused what is right and what is complexity. But in the worst case, we can say that the searching the whole set, maximum elements is what will give us the worst case. So if you have to search through the entire elements of the set, that's what is more useful than determining the time it will take, worst case time. So O notation is one of the most commonly used to express an algorithm performance in formal manner. O notation expresses the upper bound of a function with a constant factor. So specifically, if Gn is an upper bound of a function Fn, then some constant C is possible to find a value of n, let's call it n0, for which any value of n0 will result in Fn as C of Gn. So this is mathematical representation. Normally we express an algorithm performance as size, function of size of data it processes. That is, if we express size of data as n, thus linear search above we discussed has a growth rate of set size, which is f of n. So for a size of n, so O notation expresses the order of growth of algorithm in approximate terms and need not be precise. Thus, if t is the execution time of an algorithm for n equal to 10 as above versus n equal to 2024 in above linear search, then t10 will be b into 10 plus c, or t1024 will be b into 2024 plus c. B and c are constants which we have just grabbed in. But if n is much greater than b and c, then both b and c are insignificant. And so the order of a linear search algorithm is T of n. If it is 10 elements, it will be T10. If it is 1024, then order will be T24. Or we call it as O10 and O24 or ON, simplified term. So rules of O notation. Constant terms expressed as O of 1. So O of constant C is approximated as O of 1. Multiplicative constants are omitted. So if you have order O notation O of C of T and C of OT is equal to OT. So C is eliminated basically. Additional same way in uh, addition can be performed taking maximum like O of T1 plus O of T2 we call as O of T1 plus T2 to simplify, and we can further simplify max of OT1 or OT2. So whichever is greater we can take that order. Multiplication nothing changed, but it written in more compact way like O of T1 or O of T2 equal to O of T1 into T2. So if you have an algorithm whose running time grows as T of n, example, is equal to let's say 3 raised to n square plus 10 raised to n plus 10, using the four rules above for constant multiplication, addition, uh, and multiplicative constant, addition and multiplication, we can simplify this O of Tn equal to O of 3 into n square plus 10 n plus 10. So whole function of O equal to O of 3 raised to n into n square, which is equal to the highest is n square. So n square with 10 elements, we will have 100 iteration. So basically the order of time of which majority percent is consumed by n square, because 3n square and n square 100 and 300 won't make a big of a difference. The order is important. So like 100, 1000, 10,000, million. So those make a order of difference. So O notation just is the growth of time consumed or size of the algorithm growth. How the algorithm growth and how we are controlling through recursion, loops and all that to simplify the order of operation. Okay. So here is the computational complexity table we call it. So performance is usually refers to the complexity. So we looked at worst case, O notation. Now we come to computational complexity. The third, which describes the performance, which is the growth of the resource, usually time. It requires with respect to size of data. So you have a size of data to process, and therefore you have a time to process, and therefore the complexity refers to the growth rate of resource, which is time, as well as size of the data it processes. So O notation describes the algorithm complexity with respect to size of the data it processes. So let's say that O notation describes the worst case complexity in a formal manner by inspecting overall structure or overall data structure. Here are some of the typical examples of O notation. O1, fetching the first element of a set O. O log n, splitting the set of data in half, then splitting the halves in halves, etc. So this is order of log n. Traversing a set like we did linear search, On. Splitting the set of data in half repeatedly and traversing each half, O n log n. Traveling a set of data once for each member of another set of equal size, order of n square. Generating all possible subset of a set of data O to the 2 to the power n, and gathering all possible permutations of a set of data is n factorial, order of n factorial. So these are expression of complexity for specific uh, algorithm functions. Okay. Now what we can do is, if we take this and represent that in terms of numbers, we can say if n is equal to 1, what do you get? If n equal to 1m, what do we get? Etc. etc. And so you can see that it E is the exponential order. So if you have n, O log n, then you can see that if n is equal to 16, we are getting 4. 4 to the power 0. 8 to the power 0, 256. So log n is nothing but gives you n, whatever n you take a root of that, you get that almost. And that is the log, LG log represents what you call 2 to the power. So 2 to the power 4 is 16, so we get 4 in O log n. And similarly 64k, we are getting uh, 2 to the power 1.6 into 0, 160, that is. So that's the order. So for n you are getting 256, you are getting 2.5 into 10 raised to 2 e exponent, that is. For O n log n, again you are getting n equal to 0 n log n, and for 16 we are getting 6.4, and so on and so forth. So what exactly does it mean? All this computational complexity is growth rate of complexity, which we saw in previous table, right? And the same thing is described here in the order, and the same thing can be graphically depicted. So graphical representation of growth rate is like you have got Tn, n. So if n is on the x-axis, O1, O log n, On, O n log n, O n square, O2 raised to n, O n factorial. So you can see that n factorial has the highest time consuming. Whereas if you have a linear 1 or On, which is almost 20, 15 degree, and so you can see as the n increases, linear search is simpler, whereas linear search takes uh, more less time, whereas the factorial takes more time. So here 200 for n factorial. That is because suppose n factorial is, so if I have 5 factorial, I have 5 into 4 into 3 into 2 into 1, that is 5 factorial. So that takes more time than if it was just a simple 1, 2, 3, 4, 5 of n order. So time complexity, that complexity increases as we go from linear to non-linear, I would put it. And so these are the factors which shows that even for a small number like 5, it can be this, whereas for 5, it can be much smaller. So complexity growth depends on the order of the O, or the complexity of the data processing or data structure. So this is representation of complexity. And what we will do is we'll take a insert sort and do a code review of that, and then analyze insertion sort order time. So before I go into that, let me just come out of it and get into the what you call the uh, I'll have to do some kind of a let me just get into the um, see if I can have a so what I'm trying to do is I'm trying to get the access. Where is the access? Secured shell? No, not here. SSH, Cisco image. Where is this secured shell?
It's there in the extension only.
Extension? Yeah, where?
See down, down, down.
Ah, yeah, here it is. Okay, sorry. So what I'll do is I'll connect, and hopefully you'll connect me to the and let me see if I can make it bigger. Connection refused. Reconnect. Okay, let me see. probably give me a second. The system is down. Let me wake it up. System has to be woken up. The system is down. I am just booting it up. Yeah, it should connect now, hopefully. Yeah. Yeah, let me see whether I can reconnect. Yeah, so I'll be able to reconnect. Okay. Yeah, it takes some time, hopefully. Yeah, so we are here. So what I have is here, and I am going to take, so first I'll check the environment and grep for the algorithm. Do I have algo? No. So I don't have algo here. So what I'm going to do is first I'm going to, you're able to see, right, Jaymeet? Are you able to see the screen? Jaymeet? Okay, I hope.
Yeah, yeah. Actually, I forgot to unmute myself.
No, no, yeah, are you able to see this?
Yeah,
Okay, good. So
the
what I'm,
share screen, right?
yeah.
Yeah.
So now what I'm going to do is I'm going to look for the my conf. Okay, my conf. Uh, yeah. So my conf is not the one. Video. My dash export. Okay. Cat, or I can say dot slash my export. Okay. So I can say env grep algo alg. No. Okay. So let me do cat my expert. Maybe it did not work. A cat my export. Sorry. So that is where it my export. Okay. So what I am going to do is I am going to just copy this and run this. Sorry. Control Shift C. Copied. Control Shift V. Okay. So we have this algorithm, and I'm going to just export this. Sorry, this to make sure that I have the top level directory set. Okay, now if I do a env grep algo, yeah. So I have the variable set. So I can say cd to dollar algo top directory. So I am on the source directory. So I can show here we have got the example. Okay. So I can, what I can do is I can go to examples and then see what do we have here. So we have a search, right? I hope there is a search. Okay. So I can go to search folder, which is the code. So what you have here is a example. So let's take the, I will edit it and just show you example -1.c. So what we have is here is a illustration for search algorithms. So what does it have? Search algorithm, we have included in this example the library, standard library, the string library, search.h, sort.h, and spell.h. Okay. size of the string, so str size. Compare string, so what we have is a static function int compare string with pointer key 1 and pointer key 2. Both are void, so you can have any return values, whatever the return values. In this case, we are taking int return value. Okay. So you can compare the string. There is one function, and the macro size, the string size is defined as 6. Then in this case, what we are doing, comparing two strings, and what we are doing, whatever is the strcomp, which is the from the string library, you compare the pointer with the pointer to the key 1 and pointer to the key 2, and compare the two string, and if it is greater than 0, then return 1, else return -1, other when it is equal, return 0. So you got a 1, -1 and 0 as the return for comparing two strings. Now we can do, here is the data being defined as enumerations. So you have a type def, enum, and words. Uh, in this case, hop, hat, tap, bat, tip, mop, mom, cat, zoo, fax, stop, dip. These are the words. So the main program now, what it does is it has a argc and a argv variable pointing to the number of variables and the pointer to the variable. So you got target. So you got a uh, string array and a there is the search array and the target array, and both of them are size 12. 12 not size 12, rather 12 of size 6 string, 6 character, which we had defined strz. So what it does is it loads the array with data to search. So here is the str copy of so source array and target array. Source array is our search array where the array is being formed. So you have got a str copy of hop, hop, hat, hat, and so on and so forth. So it copies into the source array all the elements, string elements, which we are trying to. So this is our source array. And in this source array, what we are trying to do is search. So when you perform a binary search, you try to locate. So example, in this case, our target array, we are searching for bat, or we are searching for top, or we are searching for array xxx. Bat and top exist, so it should bat and top should work out. XXS does not exist. So when we run this program, is the string which we have in our target available on the source, and once you compare the string, that is, this is the function isort sarray 12 str size compare the string. So this will invoke the compare the string. Earlier we saw the compare string is here, so it will take the compare string and it will invoke the result. So to do this, we do for word equal to hop to word equal to less than dip word plus plus fprint std out. So this is our function. Isort compare string does the comparison by going over the entire uh, hop to dip, which is hop is the first element and dip is the last. So for word equal to hop to dip word plus plus, and keep on counting and find out when you hit that, and if you hit it, you just put the target and retrieve and answer it. So same way this will go if return value is 0, less than 0, etc., and then found at position so and so, and so this is what it will print. So you can see that this is nothing but a code which is run, which is a C code to do a search to find where it is. Now what we have is, we have here in C, usually what we do is we use it. So I can, there is a O file and a execute file. You can see exec file, object file, and then C file. C file is the source file .c, and search.make is the make file. So let's look at search.make before we do anything. Search.make. You can see that search.make define the name of the make file. So usually what happens is make file uh, is the name which is given to this file, search.make, and it defines the library, it defines the include. So directories where the libraries are there, directories where search files are there, and what it does is it will find the source file and execute by adding to it the includes headers, which is, and the libraries, and create an object file. Once you create the object file, then you will have to execute the object file. So these are nothing but algorithm top directory, which is what our directory which I had loaded, and then source and the object it generates, like in this case is sort, binary search, etc. So you can have a quick sort, binary sort, and linear sort and all that. So it executes and creates executable. And then compiler. So in this case, compiler C89, C of ANSI standard 89. We are using GCC because we are on the Linux, and Linux has a CC equal to C89. It will automatically invoke that. Libraries also belongs to this, and this is the C flags and L flags, which is nothing but what is the C file and what is the library files. So these are the flags which are given as parameters, and so the rules are set in the make file. How to create an executable file using the object file with whatever the LL, which is the library, the compiler, all the flags are set properly with -o to create the object file, and feeding all the dependencies. So make -f file name clean will clean up and start from beginning. Or if you are not using clean, then you can just dependencies. It will look at the dependencies. So it depends on the uh, source. It depends on the make the includes. It depends on the whatever make file includes. So all that it does, and finally it generates the file. So make file is a dependency file which is used for running. So what I'll say, I'll show you, instead of doing clean, I will just say right now you can see that you got executable file, object file. So all we need is make file and C file. Rest of it we don't need. So what I'm going to say, rm -r star.o. So whatever object file is I am removing. Same way rm -r, I'll remove star.exe. Okay, so we have removed the object file, and now you can see what do we have. We only have executable make file. So what I'll do is I'll make -f, and I'll do a search, SEARCH dot make. Okay, so what I'm doing is make is a function. Okay, I can even show you what is make is. Make is, if we do a man of make, it will show you it's a GNU make utility to maintain group of programs. So individual programs you can really do compilation as we did in C normally, but when you do a group of programs and combine them, it has a lot of dependencies, then you use a make. So GNU make is the, and it has got all the description. You can check the man of this, man -f, man -d, man -e, environment, and you can do a lot of other combination. So what we'll do is we'll only use make -f, and the file name we'll use is search.make. So what we expect is we will get search.make, whatever it has got, it will be able to execute that and create the file. So what it did, it invoked the compiler C89 saying that object should be sent to ex-1.0 with the file included. Source code example utils include. So it executed on ex1.c, created the object. After creating the object, it took the object and then it added what you call the main to it and created a binary. From the object file, it created executable file for the platform. So what we can see, if we do ls, you can see that we have got ex1.0 and ex1.exe, two of them. We didn't run spell.mag. If we run the spell.mag, we'll get a ex2c to ex2 ex-2o and ex2.exe. So let me do a dot slash ex-1.exe, right? If we do that, you can see that it runs the program and it shows performing binary search, and it is saying sorted bat, cat, dip 1 to 11, all that it has sorted and found that bat is at position 0, top is at position 9 and cannot find xxx. So basically it sorted and then it positioned and it identified the location. So this is one of the examples. We can do another example just for the sake of completion. So what I can do is, instead of search.make, I can do spell.make, spell.make, and so this will create another bunch of, and you can see that it has created the ex-2.0, ex2 dot exe, right? So what we can see, we can run the ex-2 dot exe, and what does it do? It it finds out whether the spell is correctly or not. So spell check, hat is spelled correctly, DOP is not spelled correctly, dip is spelled correctly. So whatever the inputs we had given in the source program, it would have, we didn't look at the source program. So I just check the ex-2.c to verify what we had included. So illustrate spell checking. So what it does, it includes all this, then it compares the two strings and returns the value. So you can see that it has the comparison and main code is there where it has a lookup, and the lookup, this is all the characters or the array copied, and then we are looking for lookup for hat. It is conducting lookup for hat, and then similarly lookup for dop and lookup for dip. So there are three calls, and that is why it is returning three answers. So we saw how it answered the three, whether the hat is spelled correctly, dop is spelled not correctly, dip. So it could figure out from the table that what are the spell checks. So these are some of the programs. So you can see that the complexity depends on the size of the elements. It depends on the uh, various efficiency, depending on how the data structure is organized. Like in this case, it is more of an array and you are using str copy, and then you are doing comparison. So these are the routines, and then they are how recursively they are done, how many times you have to operate. Those are the ways to figure out. So I think basically I have given you a picture of how insertion sort and code review we have done, and what is the complexity on this. We can look at the complexity. So in this case, if you order n, so n square by 2 n by 2 dn. So what we are looking at is insertion sort, which we looked at. It is because you have to find out the right position, and the position depends on the order n. And so n square by 2 plus n by 2 is the order, and that is being equivalent to approximately n square, because if you have n square by 2 divide by 2 multiply by 2, all those things don't matter. Square order is a important order, as you saw in the graph there. If you n square, that's what matters. So if you have one expression in that order which is squarish, then it is more order of n square. So that means if we have 10 element, we are going to have the order of 10 to the into 10 square, which is 10 to the power 2, which is equal to 100. So the complexity, formal complexity of insert search is, for a size of n, it is 100. So for a 10, it will be 100. That's what it indicates for a n square. So that's what is the complexity. And so I think I have done analysis